Welcome to Lecture 7 for Chemistry 312. This lecture is on the fission process. So we've moved on from alpha, beta, which are two particle emissions, gamma, which is a particle emission from an excited nucleus that is usually coupled with either an alpha decay or a beta decay. And now we're going to move on to the fission process, in which a heavy nucleus splits into two fission products. And we're going to see that this fission process can be induced by a particle, generally a neutron, or that the fission process can occur spontaneously, so as another type of decay route. We'll also briefly see that I can actually induce a fission with a charged particle. I need an energetic system, such as an accelerator, to achieve this. What we're going to see from the fission process is that the energetics for this fission process come from, if it's a thermal neutron, it's coming in, does not have a lot of energy, less than an eV. The energy really comes from the pairing of that neutron with an unpaired nucleon, an unpaired neutron in the nucleus. So these neutrons that come in, no charge, so they can penetrate the nucleus. They pair with an unpaired neutron. That extra pairing energy allows the resulting nucleus to overcome the fission barrier. That's why we see this unpaired neutron as an indicator of those isotopes that are in a regime where fission is energetically possible, that it tends to be those isotopes without a paired neutron that fission. We're also going to see that these fission products, they tend to have certain properties. They are heavy for the isotopes that are formed, so they'll decay by beta. They form rapidly. They de-excite through the emission initially, right after the fission process. Neutrons are released in the de-excitation process. These neutrons can then drive reactions. This high energy from the fission process, 200 MeV on average, compared to EV range or even KeV range for the other decay routes. This high energy allows the use of fission in energy systems such as nuclear reactors to produce electricity. And we're going to see that these fission products, although they primarily decay by gamma emission after beta decay, there are certain fission products that can actually emit a neutron. The energy of the daughter state that's occupied is high enough to allow neutron separation. These delayed neutrons have an importance in controlling nuclear reactors. So overall, this lecture, we're going to cover the fission process. We'll have some comparisons with previous decay routes, but we're going to focus on some of the unique attributes of fission. The readings for this lecture are Chapter 11 from Modern Nuclear Chemistry and Chapter 3 from Radiochemistry. The lecture covers a general overview of fission. We'll discuss the energetics related to fission. We'll see that energy from fission is much greater than the other decay processes we've discussed. We'll talk about the probability of a fission process occurring. We've already touched on this through the cross-section. We saw that certain isotopes have a high cross-section in terms of fission from absorption of a thermal neutron. We'll discuss that. We'll talk about fission product distributions, including total kinetic energy release, the mass distribution, and charge distribution. We'll talk about how fission has a role in nuclear reactors. It's the basis of the power generation from reactors. We'll also talk about a process where the isotope decays through a delayed neutron emission, which can induce fission. So we'll introduce delayed neutron isotopes from the fission process. And then we'll end this lecture talking about fission that's not induced from a neutron but proton-induced fission. Overview of the fission process provided here, where an isotope, such as uranium-235, which has a relatively high thermal cross-section, thermal neutron capture cross-section for the fission process. In this case, uranium-235 absorbs a neutron, goes into an excited state. That excited state has two routes of de-excitation. It can decay by emission of a photon, going back to the ground state of uranium-236, or this uranium-236 can then fission resulting in two fission products with some neutrons. And we'll discuss the fission products, the neutron emissions, and the probabilities associated with this process, along with the energetics in this lecture. Nuclear fission was discovered by Otto Hahn, Fritz Strassmann, and Lisa Meitner, and here's a picture of Lisa Meitner, back in 1938. They demonstrated that neutron irradiation of uranium resulted in some lower elements such as barium and lanthanum. They were able to perform chemical separation and showed that these fission products were indeed lower elements. They were able to induce fission in this uranium due to the odd number of neutrons. When the uranium, as we showed on the previous page, when the uranium-235 absorbed a neutron, that neutron that was absorbed paired with the unpaired neutron in the uranium nucleus, and that had additional energy, this pairing energy. That pairing energy wound up inducing fission. So odd N isotopes, heavy odd N isotopes, can undergo fission. In 1940, Georgy Flerov, who's pictured here, he was a Soviet scientist, reported that uranium-238 underwent spontaneous fission. So it fissioned on its own as basically another route of decay. Uranium-238 spontaneous fission half-life is around 10 to the 16th years. Remember, the half-life for that isotope is 4.5 times 10 to the 9th years. So the spontaneous fission half-life is much longer than the alpha decay half-life. Through investigations, several other spontaneous fission isotopes were found, and these partial fission half-lives can be anywhere from nanoseconds to 2 times 10 to the 17th year. So the partial fission half-life for uranium-238 is actually rather long. In addition to this neutron-induced fission, this thermal neutron-induced fission, fission can also occur if enough energy is supplied by the particle, and the particle has to overcome the Coulomb barrier. So a fast neutron with extra energy, can induce fission. That's what's shown here. Here's the neutron energy versus the fission cross-section. And we see for uranium-238, once we get up to 1 MeV, we start to have an increase in the fission cross-section. A proton can also induce fission. We'll discuss this at the end of the lecture. As we've already said with Georgy Flerov's work on spontaneous fission, that's fundamentally similar to alpha decay, where we get tunneling through a barrier. We've already discussed that this thermal neutron can induce fission from pairing of unpaired neutrons. That pairing produces energy, and that energy goes into the nucleus, which can be useful for inducing the fission. So nuclides with odd number of neutrons can be fissioned by thermal neutrons with large cross sections, as this is shown here for uranium-238, where we see the fission cross section high. We can demonstrate some of the energetics involved in these neutron pairing energies from Q-value calculations. So as we see here, we can have a reaction where we take an isotope, add a neutron, we get A plus 1 plus E, or the Q-value. In the case that we see here for uranium-235, the Q values are shown here. So for E, we would have the 235 plus a neutron minus uranium-236. So the 235 uranium, the Q values listed here. The neutron and the 236, that's equal to 6.5 MeV. For uranium-238, the data is shown here. So here's our Q value for mass excess uranium-238, mass excess uranium-239, mass excess for the neutron, giving us a Q value of 4.8 MeV. And then for uranium-233,
The mass excesses are shown here. Again, this is the uranium-233, the neutron, and the uranium-234. We see the difference is that for the isotope that does not undergo fission from thermal neutrons, uranium-238, the Q value is 4.8 MeV. While for the isotopes that do undergo fission, both those Q values are above 6.5 MeV. It just happens that fission requires about, the fission barrier is about between 5 and 6 MeV. So that pairing energy provides enough energy to have the isotope overcome the fission barrier and experience fission. In the fission process, the fission products of the isotopes that we're most familiar with, uranium and plutonium, undergo an asymmetric mass distribution. And that asymmetric mass distribution is shown here. And this is for uranium-233, uranium-235 in red, and then plutonium-239 in blue. We see that there's a high peak, which is consistent. That mass doesn't tend to change for the different isotopes. This lower peak, we see that the peak increases with A. We have a mass distribution ratio of high to low of about 1.4 for uranium and plutonium. And these peaks, as we've discussed earlier, they're due to shell effects from the magic numbers. The peak is close to 132, which is a doubly magic 50 proton, 82 neutron, so that'd be tin 132. Symmetric fission is suppressed by a couple orders of magnitude relative to asymmetric fission, and this is all due to shell effects. In nuclear reactions, this can also occur, and the fission will compete with evaporation of nucleons in the region of high atomic numbers. So in other words, if you make an isotope from a nuclear reaction, it can undergo fission once it's formed as opposed to de-excitation by, for instance, emitting neutrons. We'll discuss this a little bit more when we talk about nuclear reactions. So as we've seen, the location of the heavy peak pretty much remains constant for the uranium isotopes and the plutonium-239. We see the lighter peak increasing. We can also see an influence of neutron energy, as what's seen here. This is for the 235 uranium fission yield with difference between thermal neutrons and 14 MeV neutrons. The obvious change is that as we increase the energy, this middle section, the yield goes up. What we're seeing is that we're kind of washing out some of the shell effects with higher energy. As we've already seen for uranium-233, uranium-235, and plutonium-239, the fission yield distribution actually varies with the fissile isotope. With the previous isotopes we mentioned, the uranium and plutonium isotopes, that fission yield distribution was rather small. But we can imagine, as what's shown here, as I start to increase the mass of the fissioning nucleus, the heavy curve remains constant and the light continues to increase. We can imagine eventually that, particularly if we get at a close where Z is equal to 50, so Z being equal, where Z would be equal to 100, so that the fissioning isotopes would have a Z of 50, which is here. Fermium's a Z of 100. You can imagine that here we'd start getting symmetric fission. So if we look at fermium, as the mass of this fissioning system increases, the location of the heavy fission peak will start to coalesce with the light fission peak, and we can see areas on this curve where we're plotting N, the number of neutrons, against the mass of the fission fragments for the different, Z is plotted here. These are the different isotopes. we can see that those in the circles here are all symmetric. So we can definitely understand that the fission distribution is actually a function of, we've already shown it's the energy, but also the fissile isotope that's undergoing fission. Another aspect of fission products is how they are distributed. We've already talked about the yields being different, but even within a yield for a given isobar, for instance here the data is for A of 141, we have yields that can be either for specific isotopes, those are the independent fission yields, or the data that we see in the chart of the nuclides, the cumulative fission yields. For the most part, we've been working with the cumulative fission yields, which is an integration of all the independent fission yields for a given isobar. As we can see, the independent yields need to be determined for specific nuclides. These can be difficult to determine, especially with radionuclides fission products that are relatively short-lived. The data for both the independent and cumulative fission yields can be found at this web page listed here. You can find that you'll see that there's actually a relatively smaller amount of independent fission yields available. So the difference between the independent fission yields are shown here, where you have the dots on the line, and the cumulative fission yield is just the integration. And the cumulative fission yield, those are the data points that are available to us in the chart of the nuclides. We've previously described the distribution of fission products as a function of isotope. Now let's evaluate what actually happens with the nucleus as fissioning occurs. This is shown at the bottom of the figure, where the nucleus undergoes a change and eventually reaches a point where it's no longer stable. Imagine if we have charges, protons build up into the semicircular aspects of this nucleus. That charge eventually overcomes the adhesion due to nucleon-nucleon interactions. This is called the saddle point. And the rate of change of Coulomb energy is equal to the rate of change of nuclear surface energy at this point. And this induces that instability which drives the breakup of the nucleus. Beyond this point, we have fission. We have the scission point, where the nucleus divides into two fragments. The high charge in each fragment accelerates the particles away from each other, and we get about 90% of the final kinetic energy within a very short period of time, 10 to the minus 21 seconds.
Fission products are neutron-rich fragments from the nucleus, and since being neutron-rich, they tend to decay by beta emission. So those neutrons tend to get converted into protons. However, there are some areas of the fission products where these decays actually result in the liberation of a neutron. This occurs when there's an isotope that'll decay that has a Q value, say around 5 MeV, in this case iodine-137. This is from the table of the isotopes. It's part of the mass parabola for 137. We have the data here. We see that iodine-137 has a Q value of 5.8 MeV. And the daughter, the xenon-137, the data shown here, there's this SN value, the neutron separation energy, and it's at 4 MeV. So this Q value is enough, this energy is greater than the neutron separation energy. So you can imagine that if iodine-137 decays to a state that's above the neutron separation energy in the xenon, as opposed to emitting a high energy photon, the xenon can de-excite by emission of a neutron. And that's what this bar here indicates on the table of the isotopes, that this isotope will decay through neutron separation. And you can see that this is a delayed neutron. So the whole process is called delayed neutrons from fission products. So these particles, the reason that we have this energetics is that as the particles decay from an excited state down to a ground state, they go to more spherical forms. Generally, they'll give off prompt neutrons. The neutron will take away about 5 MeV. When first formed, those fission products, non-spherical, quickly emit a neutron, go to a spherical state, form a radioactive isotope, and then they tend to decay by this beta process. However, certain regions, as we see here, iodine 137, 139, and the bromine isotopes 87 to 90, can decay through this delayed neutron process. What we see is the occupation of a higher energy state and the emission of a neutron. The xenon 137, for example, its Q value is 4 MeV, and the neutron separation energy of the daughter cesium 137 is 8.2 MeV. That's not energetic enough. Same thing for the cesium 137 decay. It's a little over 1 MeV, and these neutron separation energies are close to 7 MeV. Now, this may not seem like a large fraction of neutrons. It's a little under 1% of the total neutrons from fission are these delayed neutrons, but it provides an important control of the reactor processes because these neutrons are delayed, as opposed to a neutron being emitted promptly after the fission process. For instance, iodine, this neutron has a half-life emission rate that's on the order of the decay of the iodine 137, which is around 25 seconds. Other examples of isotopes that decay by neutron emission are shown here. As an example, arsenic 87 can decay to an excited state of the selenium 87, emit a neutron. Selenium going to the bromine, same thing. Bromine going to krypton, same condition. Krypton going to rubidium, not enough energy. The krypton is only at 3.8 MeV Q value, whereas this neutron separation energy is close to 10 MeV. Bromine 90, krypton 90, same thing. So the key, if you were to look at data from the table of the isotopes, is this dark bar with the N that indicates neutron emission. And again, one of the trends is that neutron separation energy, for this case, is generally on the order of 5 MeV, and the Q value is obviously greater than that value. And as we mentioned in the previous slide, these delayed neutrons are important for maintaining chain reaction control in a reactor due to this half-life component. Though 2 seconds may not seem like a very long half-life, that emission of the neutron is much longer and it's delayed compared to the prompt from the fission process. The reason these delayed neutrons are important has to do with the fact that how fast the fission process is. About 1/10 of a millisecond is needed for a neutron from fission to react. So fission occurs, that neutron is born, that neutron then reacts with another isotope. One needs to have somewhat tight control on this, because even if you went for a tenth of a percent of an increase per generation, and you would have a 10% increase in 10 milliseconds. So you still need 100, you would basically need 100 generations for that, but it happens so quickly that 10 milliseconds, you could quickly add 10% more energy, 10% more heat to a reactor without this control. So these delayed neutrons, they all have half-lives much greater than 0.1 milliseconds. So that allows even this small fraction a means of having a little bit more control over the fission process. Now, we mentioned that for uranium-235, about 0.75% of the neutrons are delayed. And for uranium-233, it's about 0.25%, and same thing for plutonium-239. This means in some regards, uranium-235 is a better fuel for reactors, just as an example in regard to these delayed neutrons. Now, fission products also produce, they also have another influence on fission. This is, you can call it kind of a positive influence on fission. It gives off some neutrons. But there are some fission products that influence reactors because they absorb neutrons. In an example, the production of xenon-135 fission product has this isotope has a very large neutron capture cross-section, 3 × 10⁶ barns. Buildup of this isotope in reactors can actually poison the reactors and shut down the process. In regards to the fact that the buildup of the xenon-135 means that this isotope then increases, and with the increase of that value, those isotopes are capturing more and more neutrons because of its cross-section.
Some more detail on neutrons and fission in reactors are presented here, where we see that the probable neutron energy is a little under an MeV, while the average energy is about 2 MeV. This is actually used in fast reactors, since 2 MeV neutrons are certainly high enough to fission non-fissile isotopes like uranium-235. The only thing you would need to do is construct a reactor where, for a fast reactor, where the neutrons are not moderated or slowed down. That would mean high Z reflector and coolant, which is not high Z. So they often use sodium as a coolant, or even lead and bismuth. Thermal reactors need to slow down the neutrons, so they'll use water, for example, as a coolant. Anything with a lot of protons, a lot of hydrogen, graphite, carbon, that can be used to slow down neutrons. And one thing, as we discussed in the previous slide, that the power of a reactor is proportional to the number of available neutrons. The neutrons come from the fission process that creates the energy, so the number of neutrons available is a rough measurement of the number of fissions that occurred. There's a factor K, which is a multiplication factor. It's the ratio of fissions from one generation to the next. And here we've plotted multiplication factors as a function of burnup on this slide here, or as another K effective term as a function of years. And one thing they would like to do in reactor systems is have a K effective which is fairly constant over time. Once you get a K effective below 1, you are no longer able to use that as fuel. In fact, you want a K effective really of 1. You want the ratio of fissions from one generation to the next to be nice and steady. So they actually configure the reactor material, put things like burnable poisons into the core. Burnable poison is just an isotope that will absorb the neutrons and eventually be used up through the fission process. And here's an example of those K effective terms, as you see that they vary around 1 for both these figures. Something else that occurs in the fission process is damage. The very fact that these particles are being emitted damage materials and fuel within reactors. The fission process itself, the fission products recoil about 10 microns in UO2, and there's a very high local temperature, almost 3,000 degrees C in 10 nanometer diameter within the fuel. Two of the types of irradiations that can, the damage that can occur from the radiation, one is swelling, which is shown here. There's a cube. Swelling is where the axes of each side of the cube increases. And then there's something called creep, where there's no volume change, but shape change. Both these types of damage can occur in reactors. So there's actually a good deal of new research focused on trying to find materials that are impervious to swelling and creep as a function of neutron damage. The energetics of the fission process, that's what drives nuclear fission, but it's also something that we can use to evaluate which isotopes will fission and which ones won't. Fundamentally, any nucleus with an A greater than 100 can split into two approximately equal size with resulting energy. However, why do we only see fission at about 230? Because the separation of a nucleus is hindered by the Coulomb barrier. you could treat this barrier as penetration, what the particles would have to overcome in order to form two particles from a nucleus. So if we could figure out the energy from fission and compare that to the Coulomb barrier, we could evaluate the difference and find out where this fission is possible. So we would actually have to have the fission overcome the Coulomb barrier. It just turns out around uranium, both these quantities have values close to 200 MeV. The Coulomb barrier is close to 200 MeV. Fissioning is close to 200 MeV. And once the fission energy is above the Coulomb barrier, this event can occur. For comparing Coulomb barrier and fission energies, we can use our generalized value for the Coulomb barrier. Here we have the two equations. We'll use this equation for the calculations, and all we're going to compare is the Q value for fission versus the Coulomb barrier from the calculated fission products. So here we assume a symmetric fission, uranium going into palladiums, plus some energy. The Q value is 190 MeV, and the Coulomb barrier is 175. Again, for this symmetric fission, which we know doesn't occur, we see that this is energetically favored towards fission. Let's evaluate something more realistic, asymmetric fission. So we have uranium-238 going to barium plus lanthanum. The Q value is, for that reaction, is listed here, of 175. The Coulomb barrier is 164. We see that both these values result in fission. The realistic case, we need to consider shell effects. However, fission, we can also see that if there was not the shell effects, fission would actually favor symmetric distribution without the shell effects. The energetics would be more favorable. As an example, at 200 mercury has a Coulomb barrier of about 165 MeV between selected fission fragments, while the fission energy is around 140 MeV. So this, obviously, the fission energy is less than the Coulomb barrier. Mercury 200 is not expected to fission. The fission barrier is lower for uranium when compared to the mercury, so fission occurs at this point. The Coulomb barrier height increases as we go from something like mercury to uranium, increases more slowly than the increasing energy of the fission. And for this reason, spontaneous fission is only observed among the heaviest elements because the barrier for that spontaneous fission is lower. Generally, half-lives for spontaneous fission decrease rapidly with increasing Z. And here we see two figures where this demonstrates the half-life generally decrease with increasing Z. Here, as we go from thorium, uranium, plutonium, curium, californium on to element 104, we're plotting the half-life versus Z squared over A. But we see that as we go heavier in atomic number, higher in atomic number, heavier in mass, for given elements, we tend to see a general trend. However, for a given element, for instance, if we evaluate fermium, if we go to 258, from 244 to 258, we see that at 248 and 244 approximately the same, very short half-lives, and there's a high half-life peak at around 250. And this trend is repeated for the other elements. Here's another example of how we see the half-life change as a function of neutron number for elements paired, grouped into their for isotopes grouped into their elements. And we definitely see this trend as we go from uranium down to element 108. We see a definite decrease in spontaneous fission half-life. Fission can also occur through isomeric states. We talked about isomeric states with gamma decay. These often result in metastable state isotopes where the isomeric state is above the ground state and de-excites to the ground state with the emission of a photon for gamma decay. For fission, it's possible to have an isomeric state which will decay by splitting in two. And these tend to be very short, nanoseconds to microseconds, and it's a competitive process with fission. And you can basically think about these fissioning isomers are states with these second wells. So here's a primary well, here's a second well. The isotope can sit in this second well. The barrier that it has to tunnel through to fission is now much less for the isomeric fission than the spontaneous fission. And for that reason, the shape of the nucleus will change. This is why these isomers are also called shape isomers. And this exists because the shape of the isomer is different than the ground state nucleus. These fission isomers, there's about 30 of them known. They occur around uranium to berkelium. And this can be induced by neutrons, protons, deuteriums, and alpha particles. They can also result from decay. So it's possible to have one isotope decaying to a fission isomer from a parent decaying to the fission isomer in a daughter state, and then that daughter state undergoing fission. So here's some examples of the fission isomers. We can see that americium-243, the isomeric state is high enough where it's at 2 MeV, which is enough energy to get over this fission barrier. So that would be something in this figure at the top. It would be living in an area where the energy would be high enough to penetrate this barrier to fission and then go through isomeric fission. What is seen is that if one evaluates the saddle points, so a first saddle point, and this is an evaluation, the figure on the bottom left-hand corner shows energy above the first well for the first saddle point, so that would be this energy, and then the energy above the well for the second saddle point, which is shown here. That's the second well energy, and then the second saddle point energy is shown here. We see that there are changes in these trends. The second well point does not tend to change as a function of isotope. However, the relative height of the first and second well does change. This figure here shows what would happen to the nucleus, how the nuclear shape changes as it moves from one point of this fission isomer to another. So you can imagine that getting into this fission well definitely lowers this barrier, as we showed in the previous slide. The area that the area that needs to be penetrated to induce fission is much less compared to the first well condition. A final example of fission has to do with that's induced by other particles besides a neutron. And here we have an example of proton-induced fission. We see a fission mass distribution for the reaction of thorium with a proton. That produces this fission product. And here the fission product distribution for the reaction is a function of energy. And what we see is that the excitation, there's a definite influence on the fission product distribution with energy. As we see, we go from 13 MeV protons to 53 MeV protons. We start off at 13 with what looks like a typical two-humped fission distribution, as you would expect for something like thorium based upon the shell model. We're all the way at 53. We see that we get symmetric fission, which tells us that the ground state, lower energies, is really dictated by the shell model. And if we can overcome the shell model, we tend to see symmetric fission. And the amount of energy put into the system by the proton, 53 MeV, is enough to help overcome the shell model and allow symmetric fission product formation.
This lecture on fission described some important components related to the fission process. One, we described the mechanisms of fission, what occurs in the nucleus during the fission process, how the fission occurs and is driven by a distribution of charge in the nucleus, and that eventually the Coulomb barrier is enough where it overcomes the binding of the nucleons together and inducing a very energetic reaction, producing two excited fission products. And these fission products can excite through the emission of a neutron rapidly, de-excitation by emission of photons, and the formation of fission products. We discussed the types of fission reactions that can occur. One is induced by particles. The most common one that people think of are neutron-induced, particularly thermal neutron-induced reactions, as you see in reactors. Those have high neutron capture cross-sections for the fission process. We've explored on the chart of the nuclides how to determine, how to utilize these values. We've also, in this lecture, showed that fission can be induced by charged particles, proton-induced fission. You need to have an energetic system because the proton carries a charge. You need to get over the Coulomb barrier of the nucleus. We talked about spontaneous fission, where fission is just another decay process that competes with other decay processes. Spontaneously fissioning isotopes are in the high and heavy end of the chart of the nuclides. We talked about the energetics of fission, relationship between the energy, the Q value, and the Coulomb barrier. When the Q value can exceed the Coulomb barrier, fission can occur. Generally, this needs to be in a regime on the order of 200 MeV for the Q value. We talked about the probability of fission. One should remember both cumulative and specific yields. So the cumulative yield, which is also provided in the chart of the nuclides, is for a given isobar, where specific yields are for specific isotopes. And then finally, from this lecture, you should understand something about fission product distributions, particularly the mass distributions, how they're primarily asymmetric at uranium and plutonium, but they become symmetric as the mass of the fissioning isotope increases. This is driven by magic numbers of the fission products, particularly tin 132, doubly magic with a Z of 50 and an N number of neutrons of 82. And we also discussed total kinetic energy release. There's other aspects of fission that we discussed in this lecture that one should understand and helps explore and explain what occurs in the nucleus during the fission process. Here are some questions that you should be able to answer based upon the chapter. Again, these questions may show up on the quizzes. So one would be compare energy values for the symmetric and asymmetric spontaneous fission of americium-242. An example of this for uranium isotope was presented in the lecture. So what one would do is compare the Q values and the Coulomb barriers. So for the Coulomb barrier, we could use this equation, which is just related to the Z of the two fission products and the A of the two fission products. And all this says is what sort of charge one would find due to the Coulomb repulsion if the two fission products were just touching, and assuming that they're spherical. So if we want to do the other thing we need to do is talk about the fission of americium-242 and evaluate symmetric and asymmetric. Well, symmetric means splitting in two, so 242 divided by 2 is 121. So we pick two isotopes with an A of 121. And here for this example, I've selected silver and cadmium 121. I've calculated the Q value through the Q value calculator here. It's a little over 200 MeV. The Coulomb barrier is 182 MeV, and the difference is 28 MeV. So that's enough energy to obviously overcome the Coulomb barrier. For a symmetric fission product distribution, I chose one fission product being cesium-137, a common fission product, and from that the remainder would be zirconium-105. Evaluated the Q value for that, again 203 MeV.
the Coulomb barrier using this equation, a little under 180. So the Coulomb barrier is lower for the symmetric. The Q value is also lower. And the Q value is lower by a greater amount, so the overall energy is less. Nominally, one would state that fission should occur through symmetric fission because you get more energy. However, one has to overcome the shell model, the fact that the nucleons want to arrange themselves in shells. This is one of the reasons that with a high energy particle, as we saw with proton-induced fission, if you add enough energy to the nucleus, one can overcome the shell effects, and then fission through a symmetric route becomes more probable. Okay, other questions? What's the difference between prompt and delayed neutrons? Well, prompt neutron from fission means that the fission products, as soon as they're formed, they de-excite by the emission of a neutron. So that's a channel in which it's a very short time frame, as the name encourages. Prompt, as the fission product is born, it emits a neutron to de-excite and goes to the ground state. Whereas in the delayed neutron, what we saw, we have a condition where a fission product decays to an excited state of a daughter, and that daughter can de-excite through the emission of a neutron. So there's only special regions where that neutron is bound with sufficiently low energy where it can be emitted through de-excitation. And what's the difference between induced and spontaneous fission? Well, that's what we demonstrated on the very first slide of this lecture. Induced means a neutron comes in, changes the A of that isotope, so uranium-235 absorbing a neutron goes to uranium-236. That excited state of uranium-236 fissions. Whereas spontaneous fission is just another decay route. And as we saw, that Flerov was first investigated, spontaneous fission of uranium-238, where the uranium-238 decays by fission as a competitive route with alpha decay. And then finally, what influences fission product distribution? Well, there's a few things: the energy of the neutron and the target itself. Continuing with the question that was shown on the previous slide, you can compare the Coulomb barrier and Q values for the fission of isotopes of lead, thorium, plutonium, and curium. If you see a question like this, you could select which isotopes you would want to use. So you could use isotopes that are along the stable or more stable line. And the trend would be that you would see differences in the value, in the value for the Q value and the Coulomb barrier, and particularly the difference between those values, as you increase from lead to curium. The fact being that as one increases in Z, that barrier difference increases, therefore fission increases in probability. You can describe what occurs in the nucleus during fission, and that's basically demonstrated in this figure, where we have a nucleus that deforms. We reach a point, particularly here, where we form this saddle. We have two sections of the nucleus that have large positive charges. At this point, the Coulomb repulsion between these charges overcomes the near-term interaction of the nucleons, forcing the fission products to form from this nucleus. And as this breaks apart, the nucleons that are in this neck will slosh one way or the other towards the nucleus. We form these two deformed energetic fission products. They can immediately emit a neutron to de-excite. A neutron can also come from this neck. And through the de-excitation, they'll reach a more stable state. They will be the fission products, which tend to undergo beta decay. You can also compare energy from the addition of a neutron of two isotopes, for instance in this case 242 and 241 americium. Which isotope is likely to fission from the addition of a neutron? That's actually a separate question. We know that neutron-induced fission is prominent with odd number of neutron isotopes. Americium has an odd number of protons, so americium-242 has an odd number of neutrons. We would expect that this would have a more likely fission due to the addition of a neutron, and we could verify this by looking at the cross sections for the for the fission cross section for the NF reaction, and we would see that the americium-242 indeed has a much larger cross-section in comparison to the americium-241. Finally, another example would be provide calculations showing why plutonium-239 can be fissioned by thermal neutrons, but not plutonium-240. The same concept as before, the odd number of neutrons. And this is similar to an equation that was demonstrated in the lecture for uranium isotopes.
When you've completed Lecture 7, please respond to the PDF quiz and provide comments on the blog.